Hello. So today I'm going to present my final solution for the marketing campaign prediction challenge. Our objective was clear to accurately predict whether a customer will subscribe to a term deposit, maximizing the ROC AUC score. To achieve this, I moved beyond standard modeling practices. I engineered a robust machine learning pipeline that combines advanced feature engineering, a rigorous hyperparameter optimization, and a stacking ensemble architecture. So let me talk you through the four key parts of our solution: data preparation, optimization, architecture, and the final validation. So first of all, for data preparation and feature engineering, since data is like the fuel of any model, I started by ensuring our data was clean and mathematically sound for the algorithms we intended to use. So first of all, imputation, I handled missing values by imputing medians for numerical data modes for categorical data, ensuring robustness against outliers. And then I did the log transformation. I identified extreme skewness in features like balance and previous. We applied a log transformation, carefully shifted the balance feature to handle negative values. This normalized the distributions, making patterns easier for our model to detect. And then for encoding and scaling, I applied one-hot encoding to all categorical variables, expanding our feature space to 41 dimensions. And I applied the standard scaler to normalize all features. While tree-based models are robust to scale, my ensemble includes distance-based components like the meta learner, making scaling essential for optimal performance. And here is the code for it, environmental setup and data loading here. And then the advanced feature engineering part. And this part is about define and train the stacking ensemble. And then, so for next part, performance improvement strategy. So for the first question, what did I do to improve the performance of my model? So I implemented a two-tiered strategy to maximize performance, individual optimization and also ensemble generalization. So my level zero base layer, I combined five distinct models. First one is XGBoost for its powerful gradient boosting framework. Second one is Light GBM for speed and efficiency with large datasets. Third one is CatBoost for its superior handling of categorical nuances. And fourth one is Random Forest to introduce bagging and reduce variance. And finally, the extra trees classifier to add further randomness and robustness. And also, I also did so let me first show you, this is the first part of my code, and here we generated the final result. And next part I want to talk about is the hyperparameter tuning. So the reason why my hyperparameter tuning is below, I already submitted once, is because I forgot the hyperparameter tuning and also the learning curve and the confusion matrix when I first did it. So and then added after that. So now let me introduce the hyperparameter tuning part. So instead of using out-of-the-box models, I used the randomized search CV to individually optimize our gradient boosting powerhouses, XGBoost, Light GBM, and CatBoost. So for example, I tuned the learning rate, tree depth, and the number of estimators, this part. And this process yielded a highly optimized CatBoost model that achieved a standalone score of 0.7973, serving as a strong foundation. And then about the stacking ensemble part, I didn't stop at the best single model. I built a stacking classifier. So I took my optimized XGBoost, Light GBM, and CatBoost models, added random forest and extra trees for diversity, and combined them using a logistic regression meta learner. This allows the model to learn the specific strengths and weakness of each algorithms, correcting individual biases and squeezing out every bit of predictive signal. And for next part, so this is the stacking classifier part. And for next part, the assessment and fit. So for the second question, what did I do to assess or improve the fit of the model? So first of all, I employed three distinct methods to assess and improve the model's fit. First one is cross-validation. I utilized five-fold cross-validation throughout the entire process. This was my primary compass, ensuring that our reported ROC AUC score of 0.7983 was a reliable estimate of future performance. It's not just a fluke. And second, I did the learning curve analysis. So to visually diagnose the fit, I generated it by plotting the training and validation scores against the training set size. I observed that both scores converged to a high value with a narrow gap. And this confirmed that our model has a low bias and low variance. It learns complex patterns without memorizing the training data. So here is the learning curve. And then I also generated the confusion matrix using unbiased cross-validated predictions. This allowed me to inspect exactly where the model makes errors, distinguishing between false positives to and also false negatives, giving me a view of classification performance beyond just a single score. And here you can see the final part is the confusion matrix. And then I generated the result again. And that's it for my code and the presentation. Thank you for watching.